Hello, my name is Sharfin from Columbia University, and I'll be discussing our recent work on hardware-software co-optimization. With fewer actuators than degrees of freedom, underactuated kinematic chains only have access to a specific manifold in the overall state space. If the robot has multiple actuated tendons, this manifold will be multidimensional, but possibly discontinuous. We need to select appropriate hardware parameters to ensure that this manifold is continuous and sufficient for our task. Moreover, we must ensure that we can smoothly transition between states in this manifold. In this work, we approach this problem with task-based co-optimization by leveraging recent advancements in reinforcement learning. We begin by first designing a multiplexer transmission that enables efficient end-to-end task-based optimization. In extension, each link is passively driven by an elastic tendon that stretches over a pulley and is fixed to the previous link. This gives us two design parameters for each link, the radius of the pulley and the preload elongation. The chain is driven in flexion by actuated rigid tendons that are position controlled and route through all the links in the chain over either pulleys, giving us an additional hardware parameter, which is the radius of the pulley. If we pair multiple tendons, we then have an additional control parameter and another set of hardware parameters to optimize. Since the physics model of our manipulator is non-differentiable with respect to these parameters, we will need a method that enables non-differentiable co-optimization. We therefore apply Morph, an iterative training framework for design control co-optimization using reinforcement learning. First, we co-optimize both the control policy and neural network proxy of the hardware model with a hardware loss and task loss. The hardware loss is computed from a more realistic physics-based hardware model that can be differentiable or, in our case, non-differentiable. Using the updated hardware neural network, we search for design parameters that match the physics-based model to the neural network proxy. With this framework, we can co-optimize the pulley radii, link lengths, and elastic tendon preloads for a three-link multiplexer design using our transmission. With our co-optimized design, we evaluate the accuracy of our real hardware compared to simulated models over a set of reasoning experiments. Here is an example where we co-optimize the pulley radii and preload elongation. We executed the optimized control policy both open loop and closed loop using April tags to observe the joint angles. The closed loop rollouts were much faster and more accurate. A nice aspect of our multiplexer design is that we can use a slider mechanism to accurately adjust the preloads for different goals without completely having to rebuild the entire robot. To summarize, in this paper, we design a multiplexer tendon transmission for efficient co-optimization. We then co-optimize a three-link, two-motor chain. To the best of our knowledge, we are the first to do task-based co-optimization for underactuated chains with multidimensional manifolds. We then showed that our co-optimized policies can be transferred reliably to real hardware. Thank you for listening, and please visit the website and paper for more details.